Good evening, sir.
Yeah. Okay.
Hi, sir.
Yeah. Hi, Arvind.
Sir, one doubt. That's what
Hmm.
I pinged you early. Uh,
Yes, yes.
yeah, one second. I'll just share my screen.
Yes.
I've tried this, sir, for the bare metal for my board. I'm getting the error only. I don't know what.
Okay. Okay. See what is in line number 3 and what is line number 5. Can you spot the difference? The data type.
300.
What data type you used in line number 3?
Oh, okay, okay. Oh, this is the error issue.
Yes.
Yeah, yeah.
Okay.
Same project and debug.
Now just give build all. Build all. Yeah. Build all. Build all.
Okay.
So whenever you made any changes, you just have to.
Which mean this one?
Okay.
Send something. Yeah, it's okay. Yeah, it's okay.
Yeah.
Thank you, sir.
Okay. Okay, so we will start the class. Okay. What's this? Okay, so today we will see about the ADC. Okay, so analog to digital conversion. Okay, so pick we have an ADC. Okay, so on that day you said that you don't know about the successive approximation method, right? Okay, we will see that one first. I will write it in the new page itself. So this is GPA. Okay. So the first one is ADC. Yeah, so ADC is ADC. ADC is an analog to digital converter. Okay, so what is analog? What is digital? Any idea?
Digital mean on and off.
Okay.
Between that, yeah. But analog will be have a pace value, so it is like a kind of waveform. So it's non-continuous. I mean, it won't be continuous waveform.
Okay. Yeah. Is it right only? Okay. So analog is something like a continuous signal. Okay. So we have a continuous signal with respect to time. So that is what called as an analog. For example, if you take this value, something like this. Okay. This is my time period. Let's assume this is my voltage. Okay. So this is an analog waveform. Why it is analog means it has a continuous value. Continuous value in the sense you can take any time period at any interval. Okay, for example, if I take it over here, I'll get a voltage value. If I take it over here, I'll get a different voltage value. So here it will be different. Here it will be different. Okay, so I can take at any particular time period, I'll get a different value or continuous value for each and every time period over here. Okay, so this is my, let's say this is my peak voltage over here. This is my peak voltage over here, V max, something like this. Okay. Okay. So I'll get a continuous waveform or continuous signals in the analog, whereas digital, we will get something like an pulse signal. Okay. Let's say my V max is something like an 5 voltage. Okay. And this is my 0 voltage. Now what will happen here in this digital is I'll get the maximum and the minimum in the pulsator. Here I'll get a maximum. This will be minimum. Again, this will be maximum. This will be minimum. Okay. So now here what will happen? If I take a value at any given time period, I'll get only this 5 voltage. It will not be a continuous. It will be either a 0 or a 5 voltage. Okay. So there won't be any in between value or a continuous value. So that is what called as a digital. Okay. So in digital, we will have a lesser noise as compared to analog, but we will actually lose lots of informations in the digital thing. Okay. So like as compared to your Bluetooth headphone, your 3.5 mm jack headphone has a higher quality. Okay. Have you noticed that? It's because your 3.5 mm jack is having an analog conversion, okay, or an analog signal transmission, whereas your Bluetooth headphone is having a digital transmission. Okay, your data will be transmitted through the digital signals, and that will be converted back again to the analog, and you're listening to this analog vibrations. Okay, so this conversion, we will get some little bit of losses in the data during this conversion, so that digital will not have an noise, but it will lose some information. Okay, whereas analog, it has more informations, but we will have a losses as compared to that one. Okay, so that is the problem with the analog and digital. Since your boards or the microcontroller boards are digital processing. Okay, so it won't process any analog signals. It will process only the digital signals. We require the analog to digital converter in each and every board for conversion of the analog value to the digital value. Okay, for example, let's say a temperature sensor. Okay, so this is a well-known example. Is this color visible, or can I change it to some other color? Okay. Let's say my input is a temperature. Okay. So this is my temperature sensor input. My temperature is actually an physical quantity, right? That means it will have the analog value only. Okay. So now what will happen? This temperature sensor value will pass through, there is something called as an amplifier. Okay, so it is going to amplify your analog signal, and your microcontroller doesn't understand this analog signal or analog voltage. So what will happen? We will have something called as an ADC, analog to digital converter. Your temperature sensor analog value will be converted to digital value, and that will be fed to your microcontroller. Okay, so now your microcontroller will process all these things. And for example, let's assume if your temperature is greater than something like 40 degrees Celsius, okay, you're just going to turn on the cooler. Okay, so that is nothing but a fan, which is nothing but a motor. Okay, so we are going to turn on this motor. So how this motor will run? Motor will run on the analog voltage only. Okay, so now this digital value which is processed by your microcontroller will again send back to, there is something called as DAC, digital to analog converter. Okay, so this digital value will be converted into analog value, and that will be sent to your output device, whatever the output device it is. It's like, for example, if you want to send to something like a display or something like a motor to turn on and off. Okay, all these things requires a physical analog voltage. Okay, so this digital to analog converter will convert this digital value which is processed by your microcontroller into an analog value, and that will transfer back to this output device. Okay, so this is how every microcontroller will work. So your microcontroller will have an inbuilt ADC and DAC for processing the signals. Okay, so now how this analog value will be converted into a digital value. Okay, so that we will see. Before that, this ADC, okay, I think in data sheet we have seen something like an resolution of an ADC. Okay, I think you remember that. What is the resolution of our ADC? Anyone? I will remember what is the resolution of our ADC in this STM32? STM32. Yeah, we have a 12-bit ADC. Okay. Only up to 20, resolution of 12, 10, 8 or 6 bits. Okay, so that we can able to convert. Okay, so it has a maximum of 12-bit ADC. Okay, so now what is mean by 12-bit ADC is, so here we have something called as a 12-bit ADC. Okay, so that means we have 2 power 12, which is nothing but 1024, 2014, 4096 bits of values. Okay, so that much amount of value this 12-bit ADC can able to convert. Now, what is this 4096? What I will do with this value is, you can actually able to calculate the values up to 4096. I'll tell you with a simple example. Let's assume your ADC is an 4-bit ADC. Okay, instead of a 12-bit, let's assume it's a 4-bit. Okay, so if it is 4-bit, how many maximum values you can able to get? 2 power 4. What is 2 power 4?
16.
Yeah, it is 16. Okay, so it is a 16 bits. Okay, that means there is a formula for calculating the step size. Okay, step size is your voltage divided by 2 power n minus 1. Okay, so voltage is nothing but, for example, if you're using in 5 volt, 5 divided by this 2 power n is 16 minus 1, we'll be having something like an 15. Okay, so what is 1 by 15? 1 by 15 is, sorry, 1 by 3, right? So 1 by 3 is 0.33. Okay, I'll just erase this one. This is something like a 15. Okay, so this is 1 by 3, right? So we will be having a step size of 0.33 voltage. Okay. Now, what is mean by step size is for each and every 0.33 voltage, you will have 1 bit change. Okay. For example, if it is in 0 voltage, your, see, it is a 4 bit, right? So it will be 0000, 4 bits. Okay. If it is 0.33 voltage, you will be having 0001. Okay. If it is 0.66 voltage, you will be having 0010. Okay. Then what is the next value? Next value will be something like an 0.99, right? So 0.99 voltage, you'll be having 0011. Okay. And then there is something called as an 1.32. For 1.32 voltage, you will have something like an 0100. Okay. So up to 5.00 voltage, you will be having 1111. Okay. So for every 0.33 voltage, you will have one changes in your bit, digital bit. Okay. So that is what the resolution is. Okay. Now, if I have a 4-bit resolution, what will happen? What the problem is? For example, if I give an input voltage like 0.25 voltage, okay, there is a slight voltage coming from the input, right? But what will happen is, since only your bit was changing in 0.33 voltage, your 0.25 voltage will be considered as a 0 voltage only. Okay, you can't actually able to measure any value in between the 0.33 range. So that is the problem with the resolution. Okay, with a lower resolution, not with the resolution, with the lower resolution. Okay, so that is a problem. So if you have something like, let's say 1 voltage, okay, so that will still consider as this value, this digital value, rather than this. Okay, or even if I have something like a 1.25 voltage, it will be considered as this rather than this. Okay, so that is a problem with this lower bit of resolution. Now coming back to this 12-bit ADC, it is 2 power 12, that is 4096, right? So what is the step size here? Step size formula, the same thing. We will be having a 5 voltage divided by which is 4095. Is this clear, this 4-bit?
Yes, sir.
Okay. So we'll be having something like an 5 divided by 4095. You'll be having 0.0012. So we'll be having something like 0.0012 voltage, or I will just take it as 1.2 millivolt. Okay, just nothing but 10 to the power of minus 3. So I'm just converting it to 1.2 millivolt. Okay, now what will happen? For this 0 voltage, you will be having, it's an 12-bit, right? So you will be getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. For the next 1.2 millivolt, you will be having, or I will just write it entirely so that you will get the resolution value clear. So for the 0.0012 voltage, okay, you will be having 0.0001. Okay, and similarly for the next 0.0024, you'll be having 10. Okay, again similarly it will go up to 5 voltage, you will be having entire one. And we can see the difference between this 4-bit and this 12-bit. Okay, 4 bit for every 0.3 voltage, you will be having one changes. Here, every 0.001 voltage, okay, you are getting one change in the digital output. So higher the resolution of your ADC, you can able to calculate the more number of precise changes in the input voltage. Okay, so that is what called as a resolution. Okay, and can anyone tell what is the resolution for your PIC microcontroller, your ADC? Any idea? What is the ADC of PIC?
10-bit ADC.
Yeah, it is a 10-bit ADC. Okay, so this is for the PIC microcontroller. Okay, so 10-bit means you will be having 2 power 10, that is 1024 values. Okay, so 0 to 1024. So that is the resolution of your PIC microcontroller. Okay, so this is how the resolution matters for the conversion. Okay, now how this conversion will happen, or what are the ways we can able to convert this analog value into digital value. So that is what we are going to see. That is the types of ADC. Okay, so the first value or first type, it is nothing but we call it as a dual scope ADC. Okay, then the second one, we have successive approximation method. And third one, we have flash converter. And the next one, we have the binary weighted. So we have 4 different types of conversions. Okay, so that we can able to convert an analog value into digital value. Okay, we'll see one by one what it is. First, dual scope. Dual scope is the simplest way of converting the analog value into digital value, but it is a very slow process. Okay, so what will happen is here we will give the name itself says a dual scope. That means we are giving 2 different voltage for the comparator. Okay, I'll just write it over here. We have a comparator. Okay, so for our comparator, we will give an input voltage and reference voltage. Okay, this reference voltage is your analog voltage. Okay, now this Vin is nothing but this is your input voltage. Now what will happen? It will check each and every value. For example, let's say your Vin is something like 10 voltage. Okay, now in V reference, what will happen? You will just change this 0 0 0 0 0 0 0 0 0 0 0 0 and you will just send it to the DAC, digital to analog converter, and you will send it to this comparator. Okay, now what will happen? This digital value will be converted into 1 voltage and this will compare 1 voltage with 10 voltage, both are not equal. So it will just produce a 0. So once it is produced 0, it will just go to another block and okay, this is your adder block. Now this value will get increased. Okay, so now this 0 1 will be converted into 1 0. Okay, so 1 0 is nothing but it is a 2 voltage. Again, this 2 voltage will compare with the 10 voltage. It is still 0. The adder will increase. Now it is 3 voltage, 4 voltage, 5. Once it reaches 10 voltage, it will produce 1. Okay, and then this is what your voltage reference values. Okay, so this is how your dual scope will increase each bit by bit and it will check with the input voltage to the reference voltage. Okay, it is very slow process. For 10 value or 10 voltages, you require 10 cycles. Imagine for 4095 as a value, that is 5 voltage you are getting. Okay, that 4095 cycles will take to convert this analog value into digital value. That is a very slow process, right? So depends on what is your voltage, that value will get complicated. Okay, so that is the first dual scope, very slow process, very simplest process also. We will have only two input signals, that's it. And the next one is successive approximation that I will explain later because this is what we are going to use in our module. The next one is flash converter. Flash converter is something like an, it is very fast. Okay, and it is very accurate also. Okay, but the problem with this flash converter is it is an expensive. If you want to capture a micro voltage level of changes in your analog to digital conversion, then you'll be going for this flash converter. Okay, so this is very expensive. It has a larger circuit. That is the second thing. And since it has a larger circuit, it requires more power. Okay, so these are the flash converters. If you require a really a large, what to say, a conversion value, okay, then you can go for this flash converter. Like if you want to convert some micro voltage ranges of values, then you can go for this flash converter one. Okay, and then binary weighted, again it is quite similar to that of your dual scope. Okay, so we'll be checking with this binary value with your input voltage, and we will do that. It is uh, but what will happen, instead of checking everything, we will just go with a binary weighted. Okay, like it will something like a tree model. Okay, so you will have something like this as an input voltage. If it is greater, it will go left, or if it is smaller, it will go right, something like that. It will happen based on the weight value. It will either go to the left side or a right side. Okay, so that is a binary weighted. It is fast, but it is not accurate. Yes, someone said something. Is it any doubt for anyone? Okay.
Sir,
Yeah.
this ADC is a component like in it is in board, right?
Yes, it is
So we
in board.
can change also, no? We can
We
remove
can
and
change that. We can change that.
okay.
Yeah. Okay. And the next one is what we are going to use. That is an successive approximation method. Okay, so successive approximation method, which is something derived from the dual scope, but instead of checking the each and every value, we'll be actually it is a combination of a dual scope and binary weighted. Okay, so that is what an successive approximation method is. We will see that one. Successive approximation method. Okay. So the circuit for this successive approximation method is, let's have something like, okay, this is my sample hold circuit. Okay, so I'll get an analog input to this sample and hold. So now this will be given to, there is something called as a comparator again. Okay, so now this will again taken back to, there is something called as SAR, that is successive approximation register. Okay, this is actually going to increment your value. So that value will again fed to, there is something called as an DAC, digital to analog conversion, and it will send back to this one. Okay. So here, this is your V in, this is your V reference. Okay. And this is your comparator. And this is nothing but successive approximation register. Okay, so this is your sample hold circuit. Okay, so you know this DAC, this is a digital to analog converter. Okay, so this is what a circuit diagram for successive approximation method. Now, based on this input value and reference value, you will get this output as either 1 or 0. Okay, so depends on this 1 or a 0, we are just going to do a different method will happen in this SAR. Okay, so that we are going to see right now. First one, if my Vin, that is my input voltage, if it is greater than my reference voltage, okay, I will get 1 as a comparator output. If my Vin is greater than my V reference, then I will get 1 as a comparator output. Now, and similarly, if my Vin is less than V reference, then I will get 0 as a comparator output. Okay, so we have only two inputs, V in and V reference. Based on what value I'm getting, I'll get either 1 or a 0. Now,
Equal to see?
Equal to you will not get anything, so that your SAR will know, okay, this is an equal value. You will neither get 1 or not 0. Okay. Okay. Now, if it is 1, okay, that is your comparator value. If it is equal to 1, what this successive approximation register will do is it will keep current bit as same. Okay, and it will set the next bit to 1. Okay, so it will keep the current bit as same and it will set the next bit to 1 if it is equal to 1, or if it is equal to 0, change current bit to 0 and set the next bit to 1. Okay, so your SAR will perform these two operations. Okay, so if it is equal to 1, you are going to keep the current bit as same and you're going to set the next bit to 1. Okay, and if it is less than 0, then you are going to change the current bit to 0 and set the next bit to 1. Okay, what is this current bit to 0, 1 and all these things that we are going to see right now. Okay, can anyone tell any input voltage value? Any value?
12 volt.
No, just say the value from 0 to 4086.
No, I'm not getting. What question?
2025.
2025. 2025. Okay. I'm asking, say, give the value from 0 to 4086.
Okay.
Yeah. 2025. Okay, let's assume this is your input voltage, 2025. Okay. Now, initially, what will happen is, okay, this is 12-bit, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we will have one more thing. This is the 12th bit. Okay, so what I'm going to do, I'm just going to copy the entire thing. Let's keep this. Right. So initially what I will do is I will just make this last bit to 1. Okay, so let's assume this is okay, I'll take this. This is my 1. Everything else is 0. Okay. Now what is my DSC value? What is the value for this? What is the value? Which is nothing but, you know, the conversion, right? Binary to decimal conversion is nothing but 1, 2, 4, 8, 16, 32.
2046.
Yeah. It is 128. It is 256. It is 512, 1024, and 2048. Okay, so this is 2048. Okay, so this is what the value I got, 2048, which is, this is actually your V reference value. Okay, now is my V reference value is greater than my V in or less than my V in? What is my V in? 2025. Okay, I'll write it over here. My V in is 2025. Okay, is my V reference greater than my V in or less than V in?
Greater than V.
Yeah, so it is greater than my V in, right? So V in is actually 2025. But what my voltage reference value I got, it is 2048. Okay, so if my voltage reference is greater than voltage in or input voltage, this one. Okay, what is the changes I need to do? I need to change the current bit to 0 and set the next bit to 1. So this is my current bit, right? This is the bit I am working. Okay, I'm going to change this current bit to 0 and set the next bit, which is nothing but this one, to 1. Okay, so that is what I'm going to do right now. So I'll just paste it. Okay, so the step I need to do is I need to set the current bit or change the current bit to 0. So I'm just changing the current bit. This is my current bit to 0 and setting the next bit to 1. So this is my 1. Now everything else is 0. Now tell me what is the reference value?
512. Sorry, 1020.
It's 1024. Okay, so the value is 1024. Now compare this with V in. Which one is greater?
Yes, it's greater.
Okay.
V in is
So
greater.
here V in is less than V reference. Here V in is greater than V reference. Okay. So if V in is greater than V reference, what we need to do? We need to keep the current bit as same and set the next bit to 1. So this is my current bit, right? This one. Okay. I need to keep this current bit as same and I'm just going to set the next bit to 1. Okay. So I'm just going to do this thing over here. I'll just copy this. Okay. So now the condition here is I'm going to keep this. Sorry. Okay. So I need to keep this current bit as 1 and I'm going to change the next bit also to 1. Okay. So I'm just going to mm, draw this. Okay. I'm just keeping this bit as 1. Okay. It is not erasing actually. Okay. Now tell me what is the value? Since V in is greater than V reference, I'm keeping the current bit as same, whatever it is, and I'm just going to set the next bit to 1. Here my current bit is 1, so I'm just setting the same and I'm just making the next bit also 1. Okay, now tell me what is the value? 1024 plus 512. It's 1000. Is it clear what is happening or is it confusing?
$15.36.
Okay, it's clear, right? What is happening, or do you need to explain it again?
It's clear, sir.
Okay, now again, here my V in is greater than my V reference, correct? Okay, so what I'm just going to do, I just draw this instead of.
So then it's set it all will be 1 now, sir, other than the first bit. And I mean, this cycle will continue, mean.
It is 20, no, 2025, right? If all other bits are 1, it will be 2047.
No. Sir. We again keep this 1 as a, I mean, the same bit. I mean, the bit will be changed here. Now 1, current bit is 1. Again, we need to make it next as a 1.
Yeah.
Then this, it will go up to till last. Make 1, I guess.
No, it won't. See, that's what I'm saying. If you make everything 1, it will be 2047.
Mm-hmm.
but we are getting 2025, right?
Okay. Okay.
Yeah. So we have time, no issues. We'll just go step by step. 4, 5, 6, 7, 8, 9, 10. Who said 2025?
I, sir. Mohammed.
Okay. Yeah, no issues. I just okay, so this is 0, 1, 1, and I'm just going to make another bit also 1. Okay, so everything else is 0 now. Now what is the value? So it is 1536 plus 256. 1536 plus 256.
1792.
It's 1792. Okay, again my V in is greater than my V reference. Okay, so what I will do, I will again do the same thing with this. Sorry. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I'm just going to make the same 0, 1, 1, 1, again 1. It's 0, 0, 0, 0, 0, 0, 0. Now what is the value? So 1792 plus it's 128, right? Yeah, 128. 1048. 1024.
1920.
1920. Okay. So again, V in is greater than V reference. So again, add the next value. I'm not writing it again. So I'm just putting it as 1, 1, 1, 1 since I already know, right? So it's 0, 1, 1, 1, 1. This is again 1, 0, 0, 0, 0, 0, 0. So 1920,
1984.
1984.
1984.
This is again V in greater than V reference. So again, what is the next value? 0, 1, 1, 1, 1, 1. Again 1.
2016.
2016. Again, my V in is greater than V reference. Okay. 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0. Now what is the value?
2032.
It's 2032, which is less than, I mean, your V in is less than your V reference here. Okay, so here it is changing. Now what will happen? For this, you need to make this current bit to 0 and change the next bit to 1. Okay, so I'm just going to make it a 0, 1, 1, 1, 1, 1, 1. This value will become 0 and the next value will become 1. Okay, so it is now 216 plus 8. It is 2024, right? Is this clear what is happening in this line? Why I made this as 0?
Yes, sir.
So now it is 2024. So which is my V in greater than my V reference. Okay. So again, if I make the next value 1, it will be greater. Okay. So it will be 2024 plus 4. It will be 2028. Okay. Which is your V in less than your V reference. So what I will do, I'll just make this as 0 and this as 1. Okay. Now it will become 2026.
26.
Okay, so this is again V in, you made 2025. Yeah, okay. So V in less than V reference. So now what will happen? Now this again will become 0 and the next bit become 1. So this is 0, 1, 0, 1, 1, 1, 1, 1, 1, 0. So this is actually 2025. Okay, so now your V in will be equal to V reference. Okay, so now this is the digital value for your 2025. Okay, clear? So this is how your value will be changing for each and every steps. Okay, now the difference between this is the same thing your dual scope is doing, but in dual scoping, what will happen for this 2025, it will take 2025 cycles. Okay, like what will happen first, it will make this as 1 and this as 1, and it will make this each and every bit 101010. So it will go each and every bit up to 2025. So it is like a slow process, and binary weighted is something like if it is a greater or a less than, it will go. So we are just combining these two and creating a successive approximation. Okay, so now you can see we are calculating this with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so within a 12 steps, maximum 12 steps, we will find this one.
Sir, I'm not understand after 2032. Can you explain again?
Okay, so 2032 is greater, right, than your V in. Right? What is your V in? Your V in is 2025. Okay,
I
so
I get that, but after 2032, 2024, that's
uh,
what I want.
okay, so if your V in is less than V reference, what is the condition? Change the current bit to 0 and set the next bit to 1. This is what your condition, right? So what I'm doing, I'm just changing the current bit to 0 and setting the next bit to 1. Okay,
Okay, sir.
so till now it is 2016 that we already know. This is your 8. So 2016 plus 8, you will get a 2024.
Yeah, okay, sir.
Is it clear?
Yes, yes.
Or do I need to explain it again?
No, sir, it's clear.
It's clear. Okay. So this is what called as a successive approximation method. Okay. So this is how your analog value will be converted into a digital value. Okay. Clear? Yeah. Okay. So now there are multiple methods available for converting this analog value, not this value. Okay. So we have something like a polling method, and there is something called as an interrupt method. Okay, in programming, I'm saying how this value will be converted. That we will have. First one is polling method. First one is polling method. Second one is interrupt method. And third one is we have a DMA. Okay. So today we will, since we don't have much time, today we will see only this polling method, how to convert this analog value into digital value. First, I will teach only with the board. Okay, so tomorrow we will see the same polling method for, sorry, all three methods for the workpiece simulator. Okay, so today we will just discuss with the analog value with the board hardware. Okay, so for polling method, what we need to do, I'm just going to take this STM. Okay, so device driver, I'm launching it. Okay, so I'm just going to create a new project. So I'll just close this one. So file, new STM32 project. The code is very simple. Like we already know, right? What is an HAL code? HAL code is very simple. For all this conversion, that will be taken care by your HAL itself. Okay, so there is no need to put everything. We just need to follow 3 steps. That's it. Okay, so in MCU or MPU selector, what I'm going to do is let's go to this F334 board. Next, here ADC underscore hardware. Okay, so this is what my microcontroller, right? MCU for F334R8. So if you have a different board, select for that particular board. So first step is I need to go to the system core and make this RCC. High speed is bypass and low speed. I'm just going to make the crystal ceramic. This is my step number 1. As like what we did in this bare metal programming. Same thing. I need to select a clock source for this RCC. Okay, so that is the first step. The second step, here I'm not going to use any LADRs anything. So I'm not going to do anything. Directly go to, there is something called as an analog, the second one. Click this. Okay, since I have 2 ADC channels over here, ADC1 and ADC2, and DAC, I'm having 2 different DACs. Okay, so I'm just going to click this either ADC1 or ADC2. That is your wish. Okay, so first I'm just clicking ADC1. In ADC1, I'm having 3, 8, 10 different channels. Okay, so 2 ADCs, each and every ADC is having a 10 channels. So I'm just going to select the channel number 1 as an input single-ended. Okay. So once again, I'll tell you, go to this analog thing, select this ADC1 and select this input 1 as an input single-ended. Okay, leave everything as it is. We are not going to use any other channels. Here in this configuration parameters, okay, make sure your resolution is an 12-bit resolution. If you want, you can change this resolution also for a 10-bit or 8-bit or a 6-bit. That is your wish. Maximum you can able to use up to 12-bit resolution. Okay, so this change you need to make, and if you want, you can make this continuous. Okay, so make this continuous conversion mode to enable. Okay, I'll tell you what will happen with this continuous conversion mode. So change this continuous conversion mode to enable. So here my PA0 is connected to ADC1 channel number 1. That is input number 1. Okay, this is my input. Okay. Now, is there anything else? Okay, that's it. I don't need anything else. So I'm just saving this. It is asking, do you want to generate the code? I'm just clicking yes. So one is RCC clock. The next one is main config clock is not configured properly. Why? So this ADC prescaler, let's make the clock source. Okay. So make this PLL as 4 with a multiplier of 4. Okay. Make sure you are getting this ADC of 16 megahertz clock frequency. That's it. Okay. Now I'm just saving this, generate the clock. Yes. Okay. So now the code is generated for the configuration. Now you can see I have a GPIO initialization and ADC1 initialization. Okay, so if I go inside this ADC1, I'll get this ADC1, all these things. Okay, and similarly, there is one more handler. This is my ADC handler, HADC1. Okay, all your datas will be transferred through this HADC1 handler only. Okay, so your all the values will be changed. Okay, so now we are going to write the code. So code is very simple. You just need to follow 3 different steps for this following method. Okay, I'll just write it over here. Step number 1 is you need to start the ADC. I'll just maximize the speed. Okay, first you need to start the ADC. That is step number 1. And since it is a polling method, you just need to wait for the polling conversion. Okay, so that means this conversion, right? You just need to wait until this conversion is finished. Okay, so how will you know how this conversion is finished? Means this conversion will return something like HAL OK. If it returns something like HAL OK, that means the conversion is finished. Okay, so we need to check whether I'm getting HAL OK for this polling conversion. Once this conversion is finished, get the value. So this conversion will be finished, right? Now I need this value. Okay, so now get the value and store in a variable. You can declare any variable and you can able to store it. Once it is done, stop the ADC. Okay, so these 4 steps you need to follow. First, start the ADC and then initiate the conversion process. Once this conversion process is completed, get the value and store it in a variable. Okay, and then stop the ADC. That's it. A simple code. So where we are going to write, we are going to write this code inside the while of 1. So here you can see first one is I'm going to start the ADC, right? That is my step number 1. So for that, HAL underscore control space ADC underscore start. Okay. So now it will ask, do you want to start the ADC or do you want to start the ADC in DMA mode or interrupt mode? First, we are going to use only the polling method. So I'm just giving start and it is asking which ADC you need to start. So I'm just directly selecting this HADC1 because that is where my ADC conversion will happen. Okay, so this is for starting your ADC. Okay, after that, we need to start the conversion. Okay, so for starting the conversion, HAL underscore ADC underscore, there is something called as an poll for conversion. Okay, this one, POLL for conversion. So once this is, it will ask what is the ADC I need to convert, which ADC I need to convert, and what is the timeout period. Since it is a polling process, it requires some time period or delay time for this conversion. Okay, you can give any delay time. I'm just giving an 100 millisecond time I required for this conversion. Okay, now I already told you if this conversion is completed, it will return HAL OK, right? So I need to check whether I'm getting an HAL OK. So I'm just making this inside an if condition. If this particular value is double equal to HAL underscore OK, right? Then I'm just going to do some operations. That's what I'm telling. Okay. So we know what is an AL ADC pole conversion is. It will convert the value. Once it is AL okay, that means the conversion is completed. Then get this value inside a variable. Okay. For that, I'm just scrolling up. There is something called as a private variable, user code private variable. Okay. Here I'm just going to declare uint 32 underscore t of, I'm just making something like an ADC value. Okay, this is a variable I'm declaring. Okay. Now here I'll directly go ADC value equal to, okay, so I need to get the value, right? So for getting the value, the AL API is AL underscore ADC underscore get value. Okay, it will ask from where I need to get the value. This is where I need to get the value because that's where my value is converted right here. The same thing, HADC one. Okay, so I'm starting it. I've converted and as get the value. Okay, once I get this value, I'm just going to stop this ADC. So that is al underscore ADC underscore stop. Okay, class which ADC to stop? The same thing, al ADC. That's it. Okay. So after this, I'm just going to make some delay for the next conversion value. So I'm just giving something like, let's make it wait for 500 milliseconds for the next conversion. That's it. So this is for converting your analog value into digital value. That's it. Starting, conversion, get the value, stop, wait, again start it, get the next value, send it, stop it. The same thing will happen since it is in a while of flow. Okay, so I'm just going to build the code and check if there is any error. So there is zero error and zero warning. Okay, I'll just bring my board just a minute. Okay, for this, you require a potentiometer, or I'll tell you, if you don't have a potentiometer, I will tell you one simple step. If you have any wire with you, any jumper wires, something like that, connect it to 5 voltage and connect to A naught. Okay, so your 5 voltage will be converted into an analog for 4096, right? So that has to come. Or if you connect it to 3.3 voltage, that particular voltage value will come. Okay, so that is what the thing is. Because tomorrow we will see the same thing for work fee, no issues. Okay, now. Yes, okay. Is my voice clear or is it like I'm speaking from the long?
Sir, it's clear now.
It's clear, right? Okay. Yeah, so I connected my board. So now what I'm going to do, I've already built it, right? So I'm just clicking this and debug as. Okay, here I need this debug purpose. Okay, so for all other GPIOs, you can directly click the run button to run that LED or a push button kind of thing. But for this, I required an ADC. I mean, I required a debug mode. I'll tell you why it is. Okay, here. Okay, now I'm actually getting this ADC value, right? Since I don't have any display or since I didn't have any communication protocol yet covered, okay, so that I can't able to transfer the value to the USART or something like that. I need to check this value, what this ADC value is. Okay, so for that, on the right side, you can see there is something called as in variables. Okay, and if you just go to the right, there is an expression and there is one more thing called as a live expression. Okay, expression is each and every time if you run, it will just pick that particular instant value only once. That is an expression. Live expression means it will be in the live. Okay, if you change the value, it will automatically change over here. So go to live expression on the right side, click this add expression and give the same value whatever the variable you are just going to check it, give that variable and give enter. If it is correct, it will give this data type over here. Okay, if it is not, then it will just give something like an purple color or pink color, something will come over here. Okay, so we are just going to measure this value. That's what I did. Now I'm just going to click resume. Okay, I didn't get any value. Yeah, now you can see if I'm adjusting my potentiometer here. So whenever I adjust my potentiometer, my value is getting changed. Okay. So once I go to the maximum value, it is 4095. If I go to the minimum value, it will be 0. Okay. So I'll just connect it with Teams. Teams. Okay, so I have something like this. This is my sensor board. Okay. Now here you can see that this is my potentiometer. Okay, so I'm adjusting my potentiometer. You can see the value. So since I'm moving it to the left, my potentiometer value, that is my analog value, will convert it into a digital value up to 4096. That is my maximum value. And if I move it to the right, you can see the value is decreasing to 0. Okay, so this is one method. Or if you don't have this sensor or potentiometer kind of thing, what you will do is if you have an oops, I need this one. Okay, I'll just terminate this. Just a minute. Okay. So what I will do is I'll just tell you what to do. Where is my note, right? Okay. I'll go to this data sheet. Not this one. Question manual. RF 334. Okay. So where is my 5 volt? This is right side. 1, 2, 3, 4. Fourth pin. I'll just directly connect. 1, 2, 3, fourth pin. 2. Here you can see I have my A naught on this PA0. Okay. So I'm just directly connecting my A naught to the 5 voltage. I'll debug this. Switch. Resume. Yeah, you can see I'm just directly getting 4095. So what I did is I'll just show you what I did. So here you can see this is what my 5 voltage is. Okay, this particular pin. So I have just taken this 5 voltage and I have connected it to my A naught. Okay, so when I did this, like I'm just getting a 4095 because that is what my maximum 5 voltage conversion value. Okay, so is there any 3.3 voltage here? Okay, here I have a 3.
PA14.
No, not PA14. The pin exactly the next to that PA14 is 3.3 voltage. Right hand side. Left side is PA14. So this is 1, 2, 3, 4, 5, 6, 7, 8. The pin is 3.3 voltage. Okay, so now I'm just going to directly take this on the right side. I'll just connect it to 1, 2, 3, 4, 5, 6, 7, 8. The pin. Now, if I go over here, yeah, you can see it is 4038 something instead of 4096. If I remove this, you can see the value will be changed. Okay. So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, so it will be around something like 4030 something for a 3.3 voltage. Okay. So if you don't have any potentiometer anything with you, then you can just directly connect with some voltage range and you can check the ADC value. Okay. So for the same thing, like for the work we will see tomorrow, like how to connect a potentiometer and do the same program over there. Okay, that we will see tomorrow. Okay, so for this, just try it now and let me know if you're getting an output.
So
If
one
you
doubt
face,
only. That
yeah.
100 why we are giving that is V reference.
No. This 100 is nothing, but it is okay. I'll tell you what this polling method is. Polling method means your controller will wait for a particular duration of time until this process is completed. That is what called as a polling method. Okay. So here your analog value will be converted into digital value, right? So that conversion will take some time. Okay. So I'm just giving this wait for 100 millisecond for this conversion. So now your controller will wait in this 105 line for 100 millisecond until this polling is conversion. It can convert in a 20 millisecond also. Okay, that we don't know the exact timing. We're just giving something like an 100 millisecond. Wait for 100 millisecond until this conversion completed and then get that value. So this is like a delay.
Got it. Got it. Then we get output
Yeah.
from that.
Yes.
Yes. HAL. Okay. Yeah.
Mhm. Yeah.
Sir, HADC one no first channel.
Channel 1. Yeah, H means it is an handler. Okay. Then ADC 1.
Okay.
Yeah. Okay. Have we got output? Or are you trying?
So same program okay simulator use பண்ணுங்க.
புரியல. Same program?
இதே ப்ரோக்ராம் இந்த ஓகே சிமுலேட்டர்ல யூஸ் பண்ணி
ஆமா. ஆனா போர்டு மட்டும் நீங்க வேற மாத்திக்கணும். இங்க 334 இருக்கு. அதுக்கு பதில் நீங்க
சரி,
வந்து
okay.
C031
சரி,
யூஸ்
okay.
பண்ணிப்பீங்க. அவ்வளவுதான்.
Right.
ஓகே. கனெக்ஷன்ஸ்லாம் நான் நாளைக்கு சொல்றேன். எப்படி பண்ணணும் அப்படின்றது.
Right, okay.
இல்ல உங்களுக்கு ஆல்ரெடி பொட்டன்ஷியோமீட்டர் கனெக்ஷன்ஸ் தெரியும் அப்படின்னா யூ கேன் டைரக்ட்லி கிவ். சிம்பிள் பொட்டன்ஷியோமீட்டர்
Right.
கனெக்ஷன்.
Writing one.
Sir,
Hmm.
sir, I have purchased the board. So
Okay.
anything else need to like other components I need to purchase or?
No, this board itself is enough. If you want to purchase, you can get a potentiometer, LED, resistor.
Mm.
That's it.
Okay.
Yeah. And push button.
Okay. Actually, I purchased online. Then later, I didn't like cable was not there.
Yeah, cable will not come
So
with
for
this
again,
board.
yeah. So to cable, it was 45 rupees only.
Yeah,
But minimum I have to buy for 200 rupees.
Oh,
So
okay. No,
and
this
then
cable,
so I have
you can get it in local shop itself.
here in local shop it was not there. So in one electronic shop only I went there also they said minimum
No,
for
you
200
can
you have
went
to
for
purchase.
the phone mobile shop. So this, this pin is actually for the older mobiles. Like we have this button phones, right? So there, it they can use it for the charges there. You can ask them in the mobile shops.
Anyway, I have purchased, but I
Oh, you
purchased
already
one
purchased.
breadboard.
Okay,
Yeah,
okay, okay.
breadboard, small breadboard, and yeah, the two things I have purchased. That's it. So
Okay.
that's why I asked. Anything else I can purchase though.
That's it. Only this year after we'll see only the communication protocols. So for that you don't require anything. We will do everything here itself. Okay, have you finished? Or is anyone trying? Still. Okay, if you're done, then we'll see tomorrow the DMA method and interrupt method for ADC. And then we'll see the same for the work simulator also. How to connect and get an output in work simulator, that we will see tomorrow. Okay, tomorrow at 7 p.m. only. Okay.
Sir, 2 minutes. I share my screen. I have some doubts.
Okay. Okay.
So I'm using a different code.
Okay.
So yeah, this. I mean, I have selected for RCC. So this RCC I have given as per that
Okay.
we discussed in the class.
Okay.
Yeah. And then ADC I have given. So there's input 1.
No, you can give input 0 also.
But I'm unable to select.
You can't able to select that one. Okay. So it is actually configured to some other pin, I think so.
It might be here.
Yeah. See, you can. Okay. Where is PA0?
Here.
No. Yeah, that is configured to push button.
Okay. So in that interrupt 0.
That interrupt 0 is
So
configured to
it can
this.
be.
Input 0 is configured to the push button. So you can configure to this one also. Can you click and drag this configuration? Maximize this. No, this configuration. There is a line, right? Gray color line on the configuration. Yeah, just move it. Okay. So that is independent mode. Yeah, same thing. Prescaler clock divided by 4. Okay. 12-bit resolution. Yeah, this continuous conversion, make it enable.
Continuous conversion.
That's it.
Okay, sir.
So
I'll
here for
generate.
you, it is PA1 instead of PA0.
Yes.
Okay, because on the right side, you can see below this push button, you can see ADC1 input number 1.
Yeah, receive. Yeah.
Okay, so
Let's
you have
only
a
change it
PA1.
now.
Yes.
Okay. Sir.
So if you are connecting any analog devices, you have to connect it to PA1 pin instead of PA0.
Yes.
That's it. Clock configuration is okay for you. There is nothing to change. Okay, generate the code.
Option.
Just give Control S and then generate. Yes. Yeah, done.
Yes.
Okay.
It is. Yeah. Okay.
You have an
Thank
HADC
you.
one. Yes.
Okay, sir. I stop starting. Thank you, sir.
Okay. Okay, guys. So we'll see tomorrow at 7 p.m. Okay. Thank you. Bye.
Thank you. Sir.
Thank you. Bye.
Thank you, sir.
Thank you.
Thank you, sir. Bye.
Thank you. Bye.